Today, I'll be talking about, this is a chapter of my dissertation. I'm calling it The Vanishing Margins, Intersectionality, Small Groups, and Statistical Modeling. It's a project sort of rooted in the broad theories of intersectionality. A sort of very 30,000-foot view is that it's a perspective rooted in, Black and multiracial feminist theory, classically from like the Combahee River Collective, Crenshaw's pictured below. The basic idea, and I do mean sort of basic, this should not be taken as a full representation, but it's that the axes of oppression are more than the sum of their parts, right? So being a Black woman is not the same as both being Black and a woman independently. Crenshaw, I think, stated it well when she said sometimes Black women experience discrimination as Black women, not the sum of race and sex discrimination, but specifically as Black women. Before I go further, I sort of want to point to the fact that intersectionality is much broader than I will represent it here today. So McCall has this great paper in 2005 where she sort of lays out different sort of kinds of practice in intersectionality. And even these are likely not exhaustive of what you might find in literature. But she lays out sort of three big sort of commitments. One is anti-categorical, which is the notion that through intersectionality, we should sort of undermine the socially constructed categories and not rely on them for our analyses, right? The intra-categorical is basically a perspective that says the axes that we predominantly rely on are not necessarily the important ones, and we should look to the less explored intersections of various sort of identities and axes of oppression, sort of looking between the typical categories that are explored. And finally, there's the intercategorical perspective, which says we acknowledge that these categories are socially constructed, right? This should not be taken to say, for instance, that race is a natural or normal category. But we acknowledge that for practical and pragmatic reasons, they are useful for describing the social world. So we'll sort of take them practically for their utility now, but acknowledge that, they misrepresent quite a lot. And we'll specifically look at the interactions between multiple sort of standard categorical identities. Within this intercategorical approach, there's a sort of brand of quantitative work that typically uses statistical modeling to talk about some outcome of interest by modeling it with sort of interactions between different categorical representations. I just want to point out that this is the space that I'll be hanging out for this talk, right? There have been attempts to radically reconceptualize intersectionality or to somehow fix intersectionality by bringing it into a broader sort of empirical or theoretical scope. This is not that. I just want to make that very clear, right? I'm not trying to radically change anything. I'm just sort of talking about what's happening over here in this little corner. So one way of thinking about this sort of intercategorical intersectionality is that you might think of there being a spectrum from generalizability to specificity, right? So on the far generalizability spectrum, there's something like human nature, right? The assumption that there is something that generalizes across all human experience. And then towards the specificity end, we get something like subjective individualism that says, there are some things that are just entirely unique and do not generalize at all. The perspective of intersectionality, at least as Crenshaw originally formulated it, was that the typical approach that looked at independent dimensions of race and gender individually as sort of an additive was too sort of general, and that intersectionality requires us to move towards specificity, which is that we don't need to just look at race and gender individually, but instead we need to look at race and race by gender, right? So this is where we get the interaction effects. This is the notion that the experience of race is different depending on gender and vice versa, right? The experience of gender is different depending on race. since Crenshaw, the trend sort of has been to continually expand the number of categories that are used, right, beyond race and gender, and to expand the number of intersections that, potentially matter. So Glenn looked at race, gender, and class, right? This is a sort of classic and predates Crenshaw even. McCall is looking at race, gender, class across geographic place. A recent paper by Evans is looking at race by gender, by income, by education, and by age, right? And so there's this ever push towards more specificity through including many more sort of dimensions and the interactions between them. This causes some issues for our sort of standard statistical modeling approaches, right? So if we just sort of use our traditional fixed effects regression model, as the number of intersections grows, the number of coefficients that we have to include in our models increases multiplicatively, right? So in this case, if we have race by gender by class, and by race, it's just 2 categories, right? And I think I've mixed my metaphors in here somewhat. But we have 3 categories, each with 2 different options. 2 by 2 by 2 creates 8 coefficients, right? So the number of coefficients required is the multiplication of the number of categories in each of the variables, which can get out of hand quite quickly once you get 5 different dimensions, each with 3 or 4 different categories. So as the number of coefficients grows, the number of observations per sort of unique group in this intersectional matrix falls. This can lead to overfitting, right? So we dramatically increase the number of parameters in our regression model. This leads, closer and closer to a saturated model, which in turn sort of suffers from overfitting. The results may be overly dependent on the particular sample that we have and may not generalize very well. Similarly, as the sample size rather for each of these small groups falls, the coefficients that are used to describe them may become unstable, right? So we're estimating coefficients based on very few people, and so there may be large variation in our coefficient estimates across samples. And then there's also issues with multiple testing, right? So as the number of parameters we stick into our statistical regressions increase, the number that we would expect to be sort of false positives for our standard statistical significance thresholds would start to get non-negligible, right? So the Evans paper that I mentioned before that had the interactions between 5 different categories had something like 360 individual coefficients. That's, over 15 of those we would expect to be statistically significant just by sort of sampling error. So there's a current sort of gold standard approach that tries to address some of these concerns. That gold standard approach, if you will, comes from this Evans paper, and it's to model the intersectional dummies, if you will, as random effects rather than fixed effects, right? So we take our standard fixed effects equation at the top, but instead we assume that our betas come from a shared underlying distribution. This allows us to pool information across groups to inform each other group's estimated coefficient. And we get random effects shrinkage, which helps stabilize our coefficients, right? So it helps us deal with the issues of having really little information for some of these groups, and also the fact that as our sample sizes fall, the coefficients may vary rather dramatically across samples. It's not often framed in this way, but you can also think of this random effects approach as a type of regularized regression, which is sort of more popular in the data science literature than it is in the sociology literature. A regularized regression essentially adds a penalty to the overall complexity of a regression model. So it does this usually by constraining the sum of all model coefficient magnitudes to be less than some regularization factor. So there's different ways of doing this, but if we just step through it, we can sort of write down the maximum likelihood for just sort of standard fixed effects regression model. The ridge regression sort of looks like this, right? We're just adding a gamma regularization factor times the sum of all squared coefficients in the model. And because we're minimizing this whole argument, it's essentially adding a penalty to this minimization function, which shrinks all of the coefficients overall. And that's how it reduces complexity in the model. It basically reduces coefficient magnitudes across the spectrum, basically pulling everything towards zero. As sort of proof that the random effects approach is effectively the same as ridge regression, you can write out the maximum a posteriori estimate of the random effects regression model, assuming that you have normal distributions on your priors for beta, right? And we get essentially this same minimization function, except now we've got, instead of just the sum of squared coefficients, we've got the sum of the difference between squared coefficients and the overall coefficient mean mu. This is often set to 0, so this converges to the same thing as with above. And now our regularization factor, as opposed to being specified beforehand as this gamma, is now 1 over 2 times the estimated variance in coefficients, which is gotten from the posterior sampling. Okay, you can also, instead of just sort of doing the math, you can think about an epistemological basis for this analogy between the random effects approach and this sort of regularized approach. Both the pooled and random effects models and the regularized regression ask what the best estimate is, essentially when we don't have a compelling reason to think that our estimate is good, right? So when our data is sparse, what's the sort of best inference we can make, the best guess we can fill in, right? The answer from both is that you pull estimates towards the grand mean, right? So if you don't have a whole lot of data telling you that your coefficient should be a very particular number, you just assume that it looks like everything else and you fill in the grand mean. When the coefficients are instead parameterized as differences or deviations from the group mean, then you pull that coefficient towards 0, right? Which is effectively the same thing as pulling coefficient estimates towards the grand mean. So if you work out the posterior estimate, you can sort of derive this expected not exact estimate of what your predicted betas will be. And it's essentially a weighted average between the group specific mean and the overall grand mean. And the weighting are the components of variance, right? So the variance in the distributions of beta and the variance in the distribution of the observations in Y, the outcome variable, and the sample size in that specific group, right? So as our group specific sample size declines, our coefficient estimates get pulled more towards this overall grand mean. As our group sample size increases, then this estimate is pulled more towards the group specific mean. Yeah. So fundamental to this setup is the assumption of exchangeability, right? So all of the coefficients in the model are pulled towards the same target, if you will, right? So all the coefficients in the model are pulled towards the grand mean. So the estimation doesn't care about coefficients for sort of other groups that are being estimated, just that they influence the grand mean, right? So another way of thinking about this is that the groups are equally related to each other. That relatedness only comes from the assumption that they're independent draws from this underlying distribution. So it doesn't matter what order you estimate coefficients in, right? Because later estimates don't rely on previous estimates. I would argue that this creates a problem for intersectionality. It presumes that each group is equally related to each other group, right? So it assumes that if you're estimating a coefficient to describe experience for Black women, that coefficient is going to be equally related to the estimate for Black men as it is for white men. I don't think that that's how people like Crenshaw would state their theories, but that's effectively what's going on in the math. Similarly, and you can sort of work this out just sort of algebraically, but the stabilization that is argued to be a positive of these random effects approaches, that stabilization comes predominantly from majority groups, right? So if intersectionality is a perspective that's supposed to sort of highlight minority voices that typically don't get the attention that they deserve, right? I would argue this is a big problem, right? We're essentially saying in the absence of information, we're just going to assume that people look like the people who are in the largest group. That feels very against the intersectional theory to me. Just working out an example, right? If you consider just a sample of 10,000 people, distinguished only by 5 different racial categories, and these are sample sizes that are roughly proportional to the US race breakdown. So I, set these means, and then I estimated this random intercept model. I got these components of variance, and now with these different pieces, we can work out what each of these group-specific estimates will be, right? So we have our equation from before that gives us the beta hat estimate for a specific group. We can then plug in our sample sizes and our components of variance and our group-specific means. Then you do some algebra, right? You discard scaling coefficients, or constants rather. And then you can essentially write out that when you're coming up with the Native Hawaiian or Pacific Islander estimate, which is a relatively small group, you can think of that estimate as coming from 82% from what the actual mean is for Native Hawaiianers and Pacific Islanders, but also 14% of that estimate is coming from the white group, right? Just because they make up a larger portion of the sample, so they have a greater influence on the grand mean. And because we are sort of pulling this estimate towards the grand mean, we're implicitly pulling this estimate towards the white experience. So I would propose an alternative, which essentially aims at this assumption of exchangeability, and say we shouldn't assume that coefficients are equally related. We should instead assume that there's a sort of covariant structure underlying the coefficients that we're estimating, right? So I argue that we should assume that the more overlap in categories we have, we can think of them as being, you might think of them as being closer, right? If you're thinking about the geographic analogy. So I would argue that, we should, in the absence of other information, think about Black women as being closer in experience to Black men than they are to white men. There are different ways you can sort of achieve this. A sort of approach that is championed especially in these data science circles, is this Gaussian process model. And you achieve this by putting, instead of a normal distribution on the beta coefficients, you put a multivariate normal distribution, which allows you to estimate the covariance structure itself at the same time that you're estimating the group-specific coefficients. So the multivariate normal, the Gaussian process model, right, says that the betas come from this multivariate normal distribution, now with a vector of means and a covariance structure K. Mu0 is, again, a vector of prior means. Generally, that gets set to 0. K is a covariance matrix. I'm drawing more explicitly on the geographic analogy here, which basically says that the covariance is expected to fall as a function of this distance coefficient or distance matrix between coefficients. So you can think of, the distance between Black women and white men would be captured by this D coefficient. These other parameters are effectively scaling coefficients on how quickly covariance falls as a function of distance, what the minimum covariance is, and a just sort of covariance scaling. You can then just sort of put priors on these things, right? So this is a prior for the maximum covariance. We can have a prior on the rate of decline in covariance as a function of distance. And this is just an indicator here saying that, you know, if we're talking about the same unit, then we should probably use the variance in the covariance variance matrix. I'm conceptualizing this distance matrix as simply the number of shared categories, right? The number of unshared categories, right? So farther away means that you're less similar. So Black women and white men have two categories that are not shared, right? Their race is not shared, their gender is also not shared. So their distance gets set to 2. But Black women and white women, they differ on the race dimension, but are the same on the gender dimension. And so their distance is less, right? Their distance is 1. That's what's going into this estimation of the covariance function that says that we would expect the coefficient for Black women to be more similar to the coefficient for white women than it is for the coefficient to white men. Okay, so the regression coefficients from this Gaussian process model, they're no longer just a weighted average of group and grand means, but I think it's useful to think of these instead as sort of neighborhoods of regression coefficients. So we still have this sort of pooling notion, but when data is sparse, we don't want to use the overall mean, but instead we want to use the sort of mean that's weighted by a function of relatedness between groups. So if we have a really small sample of Black women, we want to lean more heavily on Black men and white women than we do white men. Yeah, go ahead.
I was in the next minute or so, maybe we'll pause a little bit because I think the structure of the talk is becoming clearer and clearer, and people may still have some questions that will help you also with the rest of the talk. So let's finish the slide and then take a few questions. Okay.
So yeah, I argue that, you know, the motivation for this essentially comes from the first line of Crenshaw's great quote, right? Which is that, you know, the last sentence is that sometimes Black women experience discrimination not as the sum of race and sex discrimination, but as Black women, right? If this motivates the intersectional perspective in general, then I think that the first sentence is a good motivation for sort of what we should assume in the absence of sort of compelling information, which is that Black women sometimes experience discrimination in ways similar to white women's experiences, and sometimes they share very similar experiences with Black men, right? And so those are the groups that we should be looking to when we don't have more compelling information. And yeah, this is a good break because now I just evaluate with simulation.
So I think Will had a question about the, and I think I had a similar one about what's the parameter of interest here and the goal of the modeling. That's a broad question, but is there some way that you could answer that would help?
I think I understand a little bit better now. What you're talking about is essentially estimating subgroup means, and I was thinking about it more complicated way. I was thinking that these were essentially, you know, interactions with the main effects. So, for example, you know, shelter in place have a bigger effect on mortality for Black women than would be predicted by, you know, the Black and female. And so then I guess you would need to translate this whole framework into a random coefficient kind of model if you were to take the parallel approach that you're starting with in critiquing. So
that's exactly right. Yeah. So this is sort of the most simplified version. There's clearly a lot of moving parts already. But yeah, in this case, it's really just the random intercept model where each coefficient represents a group-specific mean. The goal is to come up with a group-specific estimate that ideally doesn't overfit the data, that doesn't suffer as much from these instability issues, and as much as possible shares information across coefficients to come up with sort of good, more stable estimates that you might get from a sort of traditional fixed effects regression model.
Where you're estimating the means is what you're estimating, essentially.
Yep, exactly right.
Okay, got it.
Robert, could I follow up on that with a question? Just a lot of this sounds like a statistical issues where you have sparse data. If we had the complete population, then from a theoretical point of view, would all these issues disappear, or would they still be there with a complete population? I'm just trying to understand what's.
I mean, it depends then
what
on
part of
your.
this is statistical and what part of this is theoretical. And I thought maybe that question might help me understand.
It depends on your sort of philosophy of science perspective on where uncertainty is if you have full population data, right? So if you assume that population experiences, well, you don't need a statistical framework if you're just saying, person A in this population that I have full information about has this specific experience. You don't need uncertainty bounds because that's a fine statement unto itself, right? There is no uncertainty in saying that person 932 in this population had this experience. If you're thinking about sort of generalizing to more sort of philosophical and theoretical populations, right, where you might have the full population register for Sweden, but you're trying to generalize to the sort of hyperpopulation of theoretical Swedens, then you would have the same sort of concern, and the goals would be much the same. If you have the full population register, clearly your sample sizes will be very large, so the problems here will be less pronounced. But because it's sort of a Malthus problem, right? So as your sample size increases linearly, the number of dimensions that you're exploring increases geometrically, and so eventually you're going to put pressure on your sample size.
Thank you.
Sure.
So I think we're ready to go forward.
Okay. So I've walked through the sort of mathematical and theoretical justification for thinking about these problems. And now I'm just going to sort of evaluate how these different approaches actually work by simulating 100 different data sets, each with 20,000 individuals. I sort of assign each of these individuals 3 different categorical representations. The labels are purely for ease of interpretation, right? This is not meant to represent real data in any way. But I've got a sort of 3 category, something like class, right? Which has lower class, middle class, and upper class. I've got gender, which divides the sample in half. Then I've got race groups, where white is the largest race group with a sample of roughly half of the sample. And Native Hawaiian or Pacific Islanders are the smallest group with 1,000 in that race group. So this 3 by 2 by 5 creates 30 intersectional categories. Excuse me. And the sample sizes for each of these intersectional categories, these are randomly drawn, so this won't always be true, but from an average sample size of about 100 for middle class Native Hawaiian Pacific Islanders, either men or women, that would have an expected sample size of 100 to 2,000, which would be upper or lower class men or women who are white. I then simulate basically 2 data generating processes, 2 outcome variables. One is a sparse case where there's sort of only 4 group means out of the 30 are non-zero. And then I operationalize this as a multiplicative case, right? So you can model this as just 30 different dummy variables, or you can model this as main effects with then deviations, intersectional deviations from those mean effects. You get the same sort of, you can rearrange either to get the other, but basically what I'm changing here is the assumption of where the sparsity is, right? So the multiplicative case is that the sparsity is in the interactional differences from the main effects, not in the actual group means themselves. I fit 5 different models to these simulated data.
Robert, I think I'm not clear on that last. Let's just do the sparse case so I understand that. That sounds a little simpler.
Okay.
Can you just, so there's some outcome, let's say how old people are or something like that.
Sure.
And what does it mean for there to be 4 group means and that 30 are non-zero?
Right. So I think age would be a pretty bad one. So think of advantage versus disadvantage, right? Where the experience of 0 would be sort of no net positive, no net negative. Some groups here in that sort of have relative advantage, some have relative disadvantage. And there are only 4 groups out of these 30 that sort of have any advantage or disadvantage relative to other groups, right? So 26 of these different groups are sort of smack dab at 0. There are no sort of real true effects.
And the other 4 are like +1 or -1 or +3 or -2 or whatever.
Yeah, I don't have unfortunately enough time and room to go through how I did this, but I basically picked two large groups and 2 small groups, and for the within each, I gave one a large coefficient, so +3, and one a small coefficient, so +0.5, because I wanted to.
That's great.
Sort of
that makes it all concrete, so we can understand at least the sparse case. Thank you.
And then the multiplicative case basically says, you know, the race effect, the gender effect, and the class effect might be non-zero, but then the class times gender effect may be 0 more often, right? Relatively sparse. Okay, so there are 5 models that I estimate on these simulated data. The first is just the sort of standard fixed effects regression model, where each group mean is estimated with its own beta coefficient. Then there's the random effects model, right? This is the current favored solution, which just models each group mean, again, as its own unique beta, but then assumes that those betas come from a mean-centered normal distribution then there's a mixed effects approach, which is sort of a variation that is suggested by Evans in their original paper already, which basically says maybe you want this regularization, this pooling in the intersectional coefficients, but not in the main effects. So here, the alpha Ks are the effects for race, class, and gender, sort of on their own. And the beta coefficients are deviations from that. I then recombine them to come up with group-specific means. The next model is...
We're hearing an echo. I think if everybody could mute, and we'll see if we can get rid of the echo.
Testing, testing. 1, 2,
I'm thinking
3.
Ron.
Ron needs to be muted. There we go.
Okay, good. Okay, the fourth model is a Bayesian lasso, which is very similar, except instead of putting a normal distribution on things, we're putting a Laplace distribution. This pulls more of the posterior mass towards 0. I'm happy to talk more about what that looks like, but I don't have time right now. And then finally, this Gaussian process model, which is, as I said before, my sort of favored approach. I then evaluated each of these models across 5 different criteria. So mean bias, right? So how far each of these models' coefficient estimates are from the true underlying values. The mean uncertainty, so the width of confidence or credible intervals in the Bayesian cases. The mean error rate, so the proportion of confidence or credible intervals that exclude the true value. Then I also wanted some measure of coefficient stability, right, which is essentially evaluating how different these estimates are between simulations. So they're the mean variance in coefficient means across the 100 simulations. And then finally, I wanted to see if that stability is significantly different when we're sort of looking specifically at small groups, right? Because it's proposed that these are the groups that we should be worried most about being unstable. So here's the mean bias for each of my different models in 2 cases, right? So I've got the sparse case and the multiplicative case. The higher the bar, the farther away the estimates are from the true underlying values. We've got fixed effects over here on the left, which sort of as expected should be the least biased. Because it introduces sort of less prior information. There's not sort of pooling. The estimates should be sort of as close to group-specific means as possible, just based on the sample data. The bias increases as we put priors on things, right? We're essentially adjusting the estimates away from just what is suggested by the sample data and towards some sort of prior belief about what these coefficients should be. The random effects sort of has substantial bias in the sparse case, but not so much in the multiplicative case. The mixed effects has substantial bias in both cases. And then the lasso and the Gaussian process are relatively less biased. Then I look at the mean confidence intervals, and then what I find interesting here is that the amount of uncertainty is relatively similar across all the models, except for the mixed effects model, specifically when it's applied to the multiplicative case, which you can think of as sort of the best case scenario, right? The multiplicative case is specifically a data generating process that has, non-sparse main effects with then sparse interaction effects. The mixed effects model is specifically an unregularized main effect with then regularized interaction effects. So this is the case that this model essentially was built for. Similarly, the Bayesian lasso is built for having just estimates across a sparse distribution overall, and again, does well in the case that is estimated on particularly sparse data. The mean error rate, this is 0.5, right, which is where we would expect these things to be. In general, we're hanging out around 0.5. The main deviation, again, is the Bayesian lasso. So a function of the Bayesian lasso is that not only does the Laplace distribution put a lot of sort of mass on pulling coefficient estimates towards 0, but there's also sort of fairly wide tails, so that the confidence intervals themselves sort of expand a bit wider. And so in turn, we get confidence intervals that include the true values more of the time, again, in the particular cases where the Bayesian lasso are essentially fit on the data that the model is really fundamentally built for. Finally, the mean variance in means, right? This is a regression instability across simulations. The fixed effects regression coefficients are slightly unstable, I guess. They're more unstable than any of these other estimates, but we're not getting dramatic gains by any of these other models, including the Gaussian process model. It's only a slight sort of benefit from this approach, except again, the mixed effects in the Bayesian lasso, when applied specifically to the data that they are sort of most in their wheelhouse for, they do a fairly good job. The story is very much the same for if you restrict to only very small sample group sample sizes. Okay, so in the end, it turns out, so just as a summary, as the number of categories and interactions thereof expand, we increasingly head towards this subjective individualism, where each individual occupies their own unique position of subjective experience. Statistical approaches that presume discrete groups of self-same populations will necessarily break down, right? It's this Malthus idea. Groups proliferate geometrically, sample sizes increase linearly. Various statistical approaches have been proposed to deal with this problem of sparsity. There appears to be substantial variation in the kinds of results you get, depending on not just model choice, but specifically the interaction between which model you choose and what the underlying data generating process was. Unfortunately, we often don't know precisely what the data generating process was. So I find this a little concerning, right? To say that, the lasso is great, we should use it under all circumstances. I would say that that's probably only true in the specific scenarios where you have really good reasons to believe that you're in that sparse case, right? That you're not in this sort of multiplicative case where some of the coefficients, where group means aren't sparse, but the interactional coefficients may be. Yes. I think the Gaussian process models are a better fit theoretically, but from the simulations, it turns out that those theoretical gains appear to have relatively minor practical payoffs. It just performs very similarly to the fixed effects regression model, sort of across all these different metrics. The final thought is that I've specified my Gaussian process model in a very sort of simplified way, right? The distance between these coefficients are just the number of unshared categories. And it's possible that sort of much more, well, I should say, you can tweak these models, right? In getting creative with how you're specifying these distance matrices. My overly simplified version may not be doing a great job. And so the gains from the Gaussian process model, similarly to sort of the lasso model, right, may specifically depend on how closely you can match your priors about what the covariance structure look like to the actual covariance structure that you observe in the data. So yeah, in all, I think there's good theoretical justification for these Gaussian process models, but practically speaking, if you have a good guess as to what your data generating process is, you can get, apparently pretty good performance out of the Bayesian lasso and the mixed effects approaches. But in general, this choice of model seems to be fairly insubstantial. Okay, that's it. Thank you so much for your time. I'm happy to take any questions. That's my email address.
Thank you so much, Robert, for presenting very technical material in a super clear way. We have 5 minutes of a regular session. If you want to ask a question, why don't you just type your name in chat and I'll call on you. We'll see if that works. While that's pausing, I'll just ask just a process question in terms of what you're doing in your dissertation. Are you planning to apply these models to some empirical data? And if so, what have you chosen?
No, so my dissertation is a 3-chapter format, and it's looking at the interaction of quantitative methods with social construction of categories broadly construed in 3 different ways. So the first chapter is looking at racial identification in the general social survey. So looking at how actually interviewers identify, because we have a pseudo panel, because interviewers conduct multiple interviews within a year, and we can look at how they identify, over time. This is currently, I'm thinking of this as the 2nd chapter, or the 3rd chapter. The other chapter is looking at census allocation methods. So how the census essentially comes up with race numbers in the census when people don't answer that question in the census, and how those decisions impact sort of downstream statistical estimates, right? So if you want to know what the diversity index is for Oakland, you might think about constructing that estimate in different ways, only relying on the information that people actually tell the census data collector, relying on that plus the data that the census fills in, by reallocating some responses from the other category into the bigger categories, or in some cases sort of doing a full like hot deck imputation for just fully missing data. And so looking at how
that's great to get that overview. We're actually getting some questions here in chat. I have Dennis with an I.
Hey, Robert, thanks for a great talk. I was just wondering if you've tried the Gaussian process approach and compared it to the other models on a real applied problem, and if so, could you tell us what the specific problem was? I think that would help us wrap our heads around the models a little bit, and just comment a bit on how different the estimates from the Gaussian process model were from the other approaches.
I haven't. I originally thought that was going to be the next step, but I sort of didn't go to that next step when, based on simulated data where I can actually know how these models are performing across a bunch of different variations, my honest answer is that I wouldn't know really how to distinguish the performance of these models in any given trial. And so I would be really hesitant to make strong claims on how these models will perform in general based on how they perform in a single empirical example. So that was absolutely my sort of ambition for this project, was to say, like, the Gaussian process better fits the theoretical underpinnings of the intersectionality literature, plus it has all these statistical advantages, and then we can apply it to real world data and see we should clearly be doing this for all things. And that just unfortunately wasn't the answer that I got from the simulation exercises. And so I think it was sort of an honest decision to sort of stop there and say, there's a lot of uncertainty in sort of which model you should choose for a specific problem.
Great.
Yeah,
Okay, so in the
that's a great
time we have
answer.
remaining, let's take one last question from Ron.
Sorry, I'm double muted here. Yeah, this is a very basic question, but I'm not clear on whether this whole discussion and analysis of yours, is it in any way specific and particular to the intersectionality discussion, or is it very general and applicable to any problem where you're trying to estimate means in categories in which categories overlap? I guess that's my question.
Yep. It's very general and applicable to a wide variety of things, right? And so the Gaussian process model, for example, I cribbed my model specification almost exactly from a specification that looks at geographic variation, right? So if you're trying to get, say, county mean estimates, and you think that counties close by to other counties are likely to be more related than counties that are farther away, but because counties are sort of unstable, you want to have some of this underlying pooling. The Gaussian process model can really help in that instance. Sort of this notion of putting sort of more structured priors on these sort of broad random effects models that sort of have been producing these pooled estimates that in particular have been championed by people like Gelman. I think there's a lot of payoff there, and I think that's why there's a lot of excitement for these Gaussian process models. The specific interaction with intersectionality, I think, is the way in which the underlying mathematical properties of these models put more or less stress on particular group experiences. So I think it's not that exchangeability, the assumption of exchangeability is specific, but I think in the case of intersectionality, the assumption of exchangeability is particularly damaging to the theory that these models are being applied to.
Okay, on that note, let's call our official session to an end and turn off our, we can now all turn off our mute and give Robert a warm round of applause. So thank